Good afternoon, everyone. My name is Daniel Flores. I'm a student of Aeronautical Engineering at Instituto Politécnico Nacional from Mexico, and I am going to talk about inverse dynamics applied on the design of control surfaces of SAE Aerodesign regular class aircraft for the 7th SAE Brazil Aerodesign Forum. To start, the general inverse problem should be defined. Then I will present the problem adaptation to aircraft longitudinal and lateral motion in the context of the competition, its implementation, and the results for the last aircraft of Kukulcán Aerodesign, which is my team. Additionally, I will discuss the posterior work done based on this technique and present a short conclusion. Well, the general problem is the following. Obtain the force function in time for a particle of mass m that must be translated from a resting state in point A to point B within a finite time. The particle must hold its position in point B as time goes to infinity. The general problem is quite simple. If we should remember that Newton's second law of motion provides the mathematical relationship between the particle kinematics and the forces acting on it. So, we can split the equation into three relevant parts: mass, the rate of change of velocity in time, and the force function. We know mass is a constant and we want to know the force function in time. Then the answer might be on the velocity function. And we might remember that velocity is the rate of change of position in time. So the answer to the problem is the definition of a position function in time. But the question is, will my system follow any arbitrary position function as long as the equation of motion can be solved? Well, realistically, no. It is well known by the systems theory that a system, depending on its nature, will follow a determined response after being disturbed. The behavior of a system is impossible to describe to its finest detail, but we can employ a mathematical model to describe it with an acceptable accuracy. Now we can modify the equation of motion of a general system to describe aircraft motion. First, let us define the limits of the analysis. This work is focused on SAE Aerodesign regular class aircraft, which means that the flight regime is of low Reynolds number and that automatic control systems are prohibited. Of course, we could design the translational motion of an aircraft, but it isn't the purpose of this work. Rather, the motion problem has to be converted into the rotation of a rigid body, for it is understood that aircraft should possess the ability to maneuver within a flight envelope. The first case of study will be longitudinal motion, keeping in mind that we are dealing with the decoupled equations of motion of a monoplane configuration. The new motion requirement is for the aircraft to rotate from its equilibrium pitch angle up to its maximum permitted angle of attack and maintain it as time goes to infinity. The longitudinal space-state model is linear and, as Cook points out, only the short period mode affects significantly the angle of attack dynamics, which are known to have a second-order response. The angle of attack transfer function is defined just by assigning values to the damping ratio and the natural frequency of our aircraft, or even from a flying qualities criterion. It is important to mention that the input function should be as realistic as the dynamic model, for it is part of the definition of the desired kinematics. For instance, we know that a servo motor starts from an initial position and rotates to another, therefore the input equation should start in 0 and reach a steady state value after a short time, commonly 1 second, depending on the radio control configuration. The procedure to modify the general dynamic model for our purpose is shown as a comparison between the space-state model and the general rigid body equations to clarify the utilization of the aerodynamic derivatives. Of course, the moment equation is coupled with the horizontal and vertical forces equations, but we can make a modification based on the definition of the aerodynamic derivatives themselves. For instance, derivative of moment with respect to horizontal speed is 0 due to the low speed flight regime, and derivative of moment with respect to vertical speed can be replaced by the pitch stiffness slope. Therefore, the dynamic model is dependent on the angle of attack, the pitch rate, and the elevator deflection angle. The control derivative contains information about the elevator dimensions within the coefficient tau, which is the effectiveness parameter of a control surface, as most of the textbooks present. So the implementation of the technique consists of an iterative process to find the minimum value of tau for solving the dynamic model, but constraining the maximum elevator deflection to 25 degrees, which is the maximum recommended for avoiding nonlinearities and flow detachment. The final step is to associate tau with the elevator dimensions, and for that we have the effectiveness parameter plot. For the ailerons design, we can make use of the decoupled equations of lateral motion, whose moments are expressed by letter L. Cook mentions that this would be valid just for the initial 2 or 3 seconds of simulation, and after that, the roll would affect yaw. Roll motion design is slightly different from pitch for the reason that the known transfer function is that of the roll rate, which has a first-order response. The level 1 flying qualities criteria suggest achieving a bank angle of 45 degrees in a time of 1.7 seconds. By definition of the Laplace transform, we can obtain the roll angle function, which acquires a second-order divergent behavior. The latter means that the aircraft won't reach a steady bank angle, but it will reach a steady roll rate after the deflection of the ailerons to their maximum position. Mohamed Sadri's method for the design of ailerons followed this reasoning too. Of course, the roll angle won't stabilize, but it will in fact reach the desired bank angle in the specified time. The roll dynamic model can be determined as well as for pitch motion, and the algorithm of solution may be the same as the control derivative contains all the information about the aileron's dimensions. Yet it is slightly different because the control derivative itself is dependent not only on the effectiveness parameter but also on the wing geometry and the aileron span. For this work, the control derivative was calculated for semi-trapezoidal wing, which has a rectangular section and a trapezoidal section, assuming the ailerons will be located only in the trapezoidal section. We can see that the control derivative depends on the aileron tau and the inboard and outboard positions of the aileron span. Then we can perform two kinds of solution for the aileron's dimensions, fixing tau or fixing the aileron span and applying the same iterative process that was applied for the elevator. The results will be presented in the form of a sequence as well as the block diagram of the iterative process. First, the position function is obtained. Then it is differentiated once to get the velocity function. The velocity function is differentiated to obtain the acceleration function, and these three functions are substituted into the solved dynamic model. Parameter tau is iterated until the condition is achieved. The results for roll dynamics are presented to as a sequence, and we can notice that the maximum deflection condition is achieved. To conclude, I would like to mention that this technique is able to be assembled in a large iterative process to design the whole stability of an aircraft, at least for the short period dynamics, which are the most important for SAE Aerodesign, as long as the long period motion takes a large time to develop, and that the mission profile of this kind of aircraft is not longer than 3 to 5 minutes. Thank you for your attention, and don't hesitate to contact me on my email for further debate on the topic.